All right, today we are going to wrap up our discussion of new content that is related to graphs with an example of connected components. So after watching this video, you should be able to describe what connected components are, what the uses of connected components can be, and you should be able to implement an algorithm to find connected components on a graph. So let's start off with what are connected components. So looking at this picture, just thinking about what you know the word connected to mean, you might think, okay, looking at this graph, I think I see three connected components. And if that's what you're thinking, you would be absolutely correct. There are three connected components in this graph. So we can have scenarios, we can have graphs that are disjoint. So what that means is there are some components, there are some nodes that are not connected to the rest of the graph. It might be one single node that's separate from everything else. It might be one group of nodes that's separate from another group of nodes. But the nodes that are connected, the nodes that do have a path that connects them, an edge that connects them, we refer to these as connected components. So in this picture, in this example, we would say that this component here with nodes 0, 1, 2, that is one connected component. This node over to, or this cluster over to the right with nodes 4, 6, 7, and 8 is a second connected component. And down here at the bottom, 3 and 5 is our third connected component. So what are the uses of finding connected components? So typically when you're dealing with connected components, you're dealing with very large graphs, very large networks. And so it's helpful to find pieces of information that are related. It's helpful to focus in on one part of the graph at a time. So some examples might be social networks, right? Think about social networks like Facebook, Twitter, Instagram. You have millions, if not billions of users, but you only care about a small group of them, right? You have your friends. You might use connected components to find your friends or maybe your suggested friends, mutual friends, something like that. You don't care about every single person on the graph, but connected components can help you find the people you are most interested in. We can also use connected components in physical computer networks to determine which devices can actually reach one another, right? So if I'm trying to print something, okay, what printer can I actually send this file to, right? And there's all kinds of uses outside of maybe what you would traditionally think of as technology. For example, networks and connected components can be used to help track the spread of diseases and figure out, okay, where did this start? Where do we think the next breakout of this epidemic or pandemic will be? So it can be useful in some of these scenarios. The key to finding connected components is something that we've already talked about. It's something that you already know how to do. It's actually searching algorithms. So you can use a searching algorithm like breadth first search to find which components are connected to one another. So let's actually look at how we can do that. All right, so the first thing we're going to do, we're going to loop through all the available nodes in our graph, okay? Because we have a graph, we know what nodes are there. What we're trying to figure out is what is connected to what. So we're going to have a loop. We're going to, for every single node in our graph, we're going to check, okay, think about how breadth first search works. We have nodes that are either marked as explored or not explored, or maybe they're scheduled to be explored, okay? So we're going to ask the question, is this node, is it scheduled to be explored? Has it already been explored? If you're using the coloring system, you could ask the question, okay, is the color of this node still white? If that is the case, okay, so if the node is white, if it has not been explored yet, we're going to perform breadth first search using this as our starting node. And we are going to continue through breadth first search until we have found everything that we can reach. Once we finish our search, all the nodes that we found are part of the same connected component. Okay, so we can save that, we can kind of set it aside. Here's one component. However, if we pull a node out of our graph and we see, the color of this is gray or black, it's already been explored, then we don't worry about it, we skip it, we go to the next node. Okay, so let's look at an example of how this might work. So here we have a relatively small disjoint graph. There's 3 connected components. So let's see how using breadth first search we can identify these components. Okay, so we'll start, I'm just going to go in order. We'll start with node 0. Okay, we look at node 0 and we ask the question, what is the color of this node? Okay, it is still white. We need to explore this node. So we know 0 is going to be part of this component. We explore, we see what else is connected to 0. We see 4 is connected. We see 5 is connected. We're using the same coloring algorithm that we went over when we previously first looked at breadth first search. Okay, so we know 0, 4, 5. These are all connected. At this point, there are no other nodes that we can reach from 4 or 5. Breadth first search would terminate. All right, so at that point we could say, all right, we've explored 0, that's done. Let's go look at the next node in our graph, 1. When we go to explore this node, this is going to be part of a new connected component. Okay, so we're going to start with 1. We add it to a new connected component because the color is white. It's a node that we haven't looked at yet. We look for all of the siblings and children of 1. We only find node 3. Okay, so we have a relatively small connected component. At this point, breadth first search is done. We mark off 1. 1 is done. What is the next node in our graph? It is 2. So we look at 2. 2 is going to be part of a new connected component. And this breadth first search will terminate very quickly because 2 has no siblings and no children. So it is a little lonely island of a node out there all by itself. Okay. And then we could go through and say, okay, do we need to do anything with 3? No. 3, the color of 3 is not white. It's already been added to a connected component. Same with 4, same with 5. We don't need to redo search, breadth first search from those nodes. And so what we end up with are 3 connected components that match our visual representation of this graph. There is also, we're not going to do a whole lot with this, but there is also the the concept of strongly connected components. So with connected components, there is a path from one node to another node. They are connected in some way, but we're not necessarily saying that if you can go from, for example, 4 to 5, you can also go from 5 to 4. Right, we're not saying with connected components, we're not saying anything about the directionality of these connections. With strongly connected components, what we're saying is, okay, any node in this group can get to any other node. So for example, F. F can get to H, F can get to I. Same thing, I can get to F, I can get to H can get to F, H can get to I. Okay, so it's just a little bit of a stronger connection. So to wrap all of this up, so connected components, they are really useful when you have large data sets, large networks, large graphs, because you can find the elements, the nodes within that large data set that are related to one another. And to actually implement this, to actually write code to do this, you would use either breadth first search or depth first search to go through your graph and identify where those connections are.